The next paper is CTSVN, a solution for computation task scheduling in vehicle networking. This work will be presented by Zheng Fang. Zheng Fang is a graduate student at the Information Network Center, School of Computer Science, Beijing University of Posts and Telecommunications. His research interests includes computational networks and edge computing, with a current focus on applying RL to computational network scenarios. Welcome.
Okay. Okay, thanks for your introduction. Good afternoon, everyone. My name is Fang Zheng, and I am currently a master student at the Beijing University of Posts and Telecommunications. I'm very pleased to share my paper. My report is divided into 4 sections: research background, research design, algorithm design, and experimental results. And the first is research background. Well, in recent years, with the development of the Internet of Vehicle, a variety of new in-vehicle vehicle application devices have emerged, such as different vehicle and human behavior prediction, travel environment, route navigation, and auto driving. This device function can be better provide people with convenient ride and driving service. However, these testers has different computing requirements due to the various demands of the computing scenarios, which lead to a different difficult computing power requirement. In traditional solution, we have defined 3 distinct approaches. The first in the edge computing solution, which offer vehicle-based text that cannot be processed by the vehicle itself to edge-based session. Primarily address the issue of the insufficient computing power in vehicle system. However, due to the limited region of the fixed base station and the high deployment cost, particularly in area where sparse base station converge, the limitation become more pronounced. The section is the cloud edge comparative computation solution, which considers the size and the latency sensitivity of the test after the stellar and latency-sensitive test to base station computing and transmission ledger. And ledger latency insensitive test of the to the cloud computing. However, the solution only discloses text by the size and does not consider the text diversity. The third approach considers the text table, introducing additional computing nodes such as the amount area vehicle or satellites into the edge computing scenario as needed to address capable in computing capability. Which are useful in special scenarios. This approach cannot fully address the computing requirement of the vehicle to everything scenario. Driven by this demand, we proposed the CTSVN framework. This framework has 2 core features. First, it introduced the concept of the ubiquity into the field of the edge computing, incorporating almost all possible nodes in the vehicle network into the computing power network rather than the physical computing network node of the traditional cloud edge collaboration system, thereby enrich the table of the atomic operation in the network and allow the vehicle to select cooperating computer nodes. To better enable the first feature, we introduced the second feature. We transformed the existing QoS-based hardware matching in the physical matching mode based on the matching degree. Through the DRL learning, we importantly mapped the relationship between the test feature and the node compatibility to enhance the filter tolerance of the match process. In summary, this framework adapted to high complexity vehicle network scenarios by increase the diversity of the computing node. While the node test mechanism within the framework ensure that the different computing network can be effectively offered to the cooperating computer nodes. Let me introduce the network model. As shown in the figure 1, this system considers a computing network composed of the vehicle nodes, base station nodes, UAV nodes, and satellite nodes, represented by the set 1. The second set represents the location information of the node key at time A, and as the vehicle moved along its trajectory, it generates a test at each time slot, which can be represented by the set 3. Here, the first denotes of the test data size in bits. The second represents the mechanism tolerable delay of the test in milliseconds, and the last is the test table identifier. Different tests require different computer node for computing using the varying size and latency. The computing model proposed in the purpose may cover two key parts: the data process and the wireless channel. This is the delay model. The delay model proposed in the paper address the heterogeneous node characteristic in vehicle to everything computing network establish a unified yet different delay calculation framework. The query of the model decomposes the total task delay into components: computational delay and the transition delay, and perform adaptive calculation based on the node type. For conventional nodes such as the vehicle base station and the journeys, computation delay is determined by the text data, computing density, and the node computing power, while transmission delay follows the channel system, where the effect rate integrates the couple effect of the bandwidth, single to noise ratio, and the computational density. Satellite nodes due to their high bandwidth characteristic receive special segment. Transition delay is simplified to incremental rival propagation delay, which is so dependent on the orbital altitude and ground distance. Our main goal is to maximize the system quality of the service, which include the total system delay, task completion rate and the task matching degree. The follow are the rate optimism problem. Where constraint C1 is the computing reachability constraint means that only nodes with a single two noise rating above the threshold are allowed to participate in text allocation. Constraint C2 indicates that the process delay of each text must not exist to the maximum tolerated delay. Constraint C3 states that text must be processed by the cooperating node. In the computing network scenario, the MIPPO algorithm operates based on the actor and critical agriculture. Each agent first perceives environmental state information that include vehicle location and speed. Text data science, text deadline, task table identifier, node computation speed, signal transition power, and more. This information is then passed to the actor and corrector network. The actor network generates actions based on the state information. The goal of the reward function is this scenario is the encourage agents to select the appropriate tangent computing nodes to process the text while millions test process delay and cost. In practice, the cost of the acquired values algorithmic power is different, so we incorporate the different difficulty of the algorithmic power equation into the design of the reward function. The reward function is designed specially consider three factors: test process delay, node selection cost, and the test mature degree. Test mature influence MIPPO decision through the dual paths. First, direct reward signal where mature service as the primary term of the word function of the worker function to the insensitivity correct match. Second is indirect delay control where good match reduce subsequent delay and indirectly enhance long-term gains. This design allows intelligence and to the automatic balance immediate measure reward with long-term delay gains when exploit. Well, this is the awesome flow design. Let's look at the result. In figure 1, three sets of the experimental scheme are set up. The CTSVN scheme includes all tables of the computer network nodes, while the other two schemes only include parting table of the computer node. As shown in the figure, since the diverse table of the nodes in the CTSVN scheme, the system quality of the queries is improved by 4% and 13%. Compared to other two schemes, the system's quality of the quality of the service is improved by 28%. In figure 2, the introduction of the matching algorithm directs different table of the text to appropriate computing nodes to process, leading overall improvement in the system performance. We also compare to the performance between different MIL algorithms, and in in fine grained state, the MIPP algorithm improves the quality of the service by 15.4% over the IA2C algorithm due to the introduction of the network. The CTSVN framework supports different table of the atomic node to the atomic node to the measure into the algorithm network, and also support different kinds of the computational tests with the different requirements to offer to the major atomic node. So the CTSVN framework have a good node scalability and test scalability. The CTSVN framework have four key advantages. First, it creates a more collaborative computing environment for distributing tests among nodes such as workers, vehicle, base station, drones, and satellites. Second, if a computing node fails, tests can be quickly reassigned to other accessible nodes to ensure presence. Third, the introduction of the drone and the satellite node not only compensate for the insufficient ground network coverage, but also enhance the readiness of the computer network. Finally, computing node can be deployed according to the need of the computing scenario or exists computing node within the scenario can be utilized, make deploying more convenient. That's all. Thank you.
Okay, thank you. Any questions?
Okay. You mentioned the conception the task matching degree in your framework. Could you please explain how you apply it in your framework?
Okay, good question. Thank you. Let me see. When I train my agent, I obtain the table of the test and the table of the node, and get into the network. Get into the network from the environment. If their table is matched, I will give him a positive score to his Q network. If otherwise, I will give her a negative feedback. I guess in the future, I feel in the future in the complex scenario in the future, there won't be just two tables of the feedback, and such as positive and negative, but rather a diverse degree of the matrix. Different node and different tester will have different degree of the matrix.
Okay. The second.
Sorry, I think we have the discussion continue offline because we will run out of our time. Okay. Thank you.
Oh, thank you.
Okay, the final paper is understanding the long